I drew this out ahead of time to save time for me writing it out since there's so much writing and I'm kind of limited on my YouTube video length. So let's go ahead and go through our three-field calculation to isocentered calculation. Prior to this, we talked about an APPA setup where we maybe had a tumor midline, our isocenter was midline, and we had one field from the ant, one field from the post. This dose distribution gives us a column of dose with hotspots, ant, and post, which the only way to decrease these is to increase the energy or the patient loses weight or decreases the thickness. Okay, good parts about this are it's easy for the therapist, it's a fast treatment, there's only two fields, and you can be off in the vertical direction, 2 or 3 centimeters and still not really underdose or affect the dose at your target. The bad news is that because of this column of dose, all these tissues, anterior and posterior, are really treated at a higher dose than our target. And in the case of a rectum, we don't want this because often for a rectum, in this case, my patient geometry is simulated supine, so my anterior is here, my posterior is here. This is right, this is left. In the case of a rectal treatment, we have small bowel on the anterior side, so we don't just want to blast through all of the small bowel. It creates a lot of side effects for the patient that can be avoided. So what we're going to do is we're going to have a three-field arrangement where we have a right lat, a left lat, and then a PA, and try and avoid or minimize my dose to the small bowel. My calibration conditions that we're going to reference are up here. Okay, so we are at 100 centimeter SSD at D max for our 1 centigrade per MU for a 10 by 10 field size. For my fields, I have 15x from the laterals, and then I have 6x from the PA. 6x for two reasons. We want to make sure we have adequate buildup in the dose, adequate buildup distance here, as well as we want to mitigate any sort of transmission through our small bowel by using a decreased energy. Because of the three-field arrangement, I'm going to end up getting, if I don't have wedges in here, I'm going to end up having hot spots posterior where the intersection of the PA and the laterals meet. So to mitigate those hot spots, I am going to add 45-degree wedges. 45-degree wedges, again, are just my assumption for this calculation. Your wedge always depends on patient geometry, isocenter location, calc point location, etc. There's an equation where you can calculate the wedge angle for a wedge pair. If you have two fields that have wedges like so, this is considered the hinge angle, or alpha. Your wedge angle is taken as 180 minus alpha divided by 2. And that gives you, again, it's a rough starting point. It's not necessarily your final answer. These are my beam conditions, or my field geometry for my three fields. The right and left lat are parallel opposed fields, so they'll be identical. My collimator equivalent square, my blocked field equivalent square, since I'm going to have an MLC blocking part of the field. My energy, and then my depth, I'm assuming for my patient geometry, is 30 centimeters left to right and 20 centimeters ant to post. So if I'm calc to midplane, midline, 15 centimeters for the lateral, and then I have 10 centimeters from the PA, and I have 6x. My beam, the last thing that we're going to want is beam weighting. My beam weighting, I'm delivering 50% of the dose from the PA, and I'm delivering 25% of the dose from each of the laterals. My physician prescribes to me deliver 180 centigrade times 28 fractions to 50-40 centigrade at isocenter at 100%. So my normalization is at 100%. When I set up my monitor unit equation, I have my dose divided by my two output factors, the collimator scatter factor, the phantom scatter factor. I have my depth component, my tissue maximum ratio. I have the isodose line, which is 100%. In this case, I have an inverse square factor since I'm calculating to 100 centimeter SAD, but my calibration was done at 100 centimeter SSD. The last thing I need is I need a wedge factor. Okay, there's not going to be a tray factor because my MLCs are going to be blocking my fields. Again, you can use the beam data tables that I imported to look up all of these numbers and verify that I didn't make any major mistakes. But basically, if we take for the right MU for the right lat, if I take 0.25, 25% times 180, my prescription dose, I get 45 centigrade. All right. My two output factors are 1.021, 1.003, TMR 0.774. My normalization factor is 1.0 because I'm at 100%. My inverse square factor, remember my inverse square law is source to calibration distance divided by source to point distance squared. 102.8, that's my source to calibration distance. I'm at 100 centimeter SAD, my source to axis distance squared. And then I have 0.52 for my wedge factor. careful with the wedge factors. The wedge factors change with field size and depth. Most physicists don't want to specify them for depth, so they just change it for field size. That's how they're listed in our data book. So I had to interpolate the wedge factor between a 10 and 15 centimeter equivalent square field size. Once I plug and chug all these in the calculator, I end up getting 103 monitor units from the right lateral. Since left lat and right lat are identical fields, I get 103 for the left lat. My monitor unit for the PA, I take 0.5, 50% of the beam weight is given, so 180 times 0.5 is 90. These are all of my beam factors. My inverse square law, again, is 101.5, my source to calibration distance, divided by 100, which is my source to point distance in the plan, squared. I don't have a wedge factor for the PA, so I just get 1.0. After I plug and chug through here, I have my final monitor units are 106 MU. So from the laterals, I'm delivering 103 MU. From the PA, I'm delivering 106 MU. Why are these so close? If I'm delivering twice the amount of dose from the PA as I am from the laterals, well, it's so close because I have a wedge factor. I have a wedge that attenuates roughly 50% of the beam, 0.5. Okay, so to account for that 50% attenuation by that hunk of metal that's sitting in the beam, I have to double the intensity of the radiation. So without the wedge factor, this would be divided by 2, okay, which makes sense then. It would be half of this, since I'm delivering half the dose of my PA, but I'm not, but it's not divided by 2 because I have a wedge. That's what makes the monitor unit so large. So 106, 103, that's what you should get. I would encourage you to try it first and then go back and listen to everything. Let's say I want to calculate the dose to the small bowel. Okay. Final add-on for this video is what happens if I want to calculate a dose 5 centimeters anterior to my isocenter located in the small bowel. Now I get that you're going to have scatter from the right and left lat. Okay, you're going to have scatter from the right and left lat. Even if the beams come in like this and they're outside of the field, yes, you're going to have dose that scatters out. We're going to totally ignore that for the sake of this calculation. Okay, I want to know from the PA beam how much dose to that 5 centimeter point am I getting just from the PA. So my small bowel dose from the PA, I'm going to rearrange this formula. So I'm going to take everything on the bottom and I'm going to multiply it over times my monitor units. So my monitor units from the PA were 106, 1.026 for S sub C, 1.014 for S sub P, 0.793 for my TMR. My normalization factor is 1.0. I have no wedge factor. Next is my inverse square factor. Source to calibration distance, 101.5 divided by source to point distance. My source to point distance is going to be 100 centimeters SAD plus 5 centimeters. So it's 105 centimeters. Plug and chug this, and you end up getting 81 centigrade. Over the total course of treatment, we have 81 times 28 fractions.